The optical rotation of sugar in industry is a quick way to determine the concentration of sugar in a solution. If 20 grams of sugar dissolved in 100 ml of water and placed in a 40 centimeters sample tube gives an optical rotation of plus 53.2 degrees, what would be the concentration of sugar that gives an optical rotation of 13.3 degrees using the same sample tube? So let's write down the information that was given in the question. The length of the sample tube was 40 centimeters. So the path length L is equal to 40 centimeters. But we know that 10 centimeters is equal to 1 decimeter. So 40 centimeters is equal to 4 decimeters. Then, so in the first part, what we need to do is to first calculate the specific rotation of the sample. However, we were given the mass of the sample as 20 grams, and we were also given the volume of the sample. It was placed in 100 ml of water, so the volume is 100 ml. That means we can calculate concentration, which is equal to mass over volume, and this is equal to 20 grams over 100 ml, and 20 over 100 is equal to 0.2 gram per milliliters. But specific rotation is giving us the angle of rotation divided by concentration times the path length. So the angle of rotation was given as 13.3. Sorry, the angle of rotation was given as 53.2 degrees. So here's 53.2 degrees divided by the concentration, which we got as 0.2 times the path length, which was 4 decimeters. And this is equal to 66.5 degrees. However, he's saying that what will be the concentration of sugar that gives an optical rotation of 13.3 degrees. So what we do is that we can make concentration the subject over here. So in making the concentration the subject, we know that concentration is equal to the observed angle of rotation divided by the specific rotation times the path length. And in the new situation, the observed angle of rotation was 13.3 degrees. So this is equal to 13.3 degrees divided by the specific rotation. And we got the specific rotation as 66.5 degrees. Then times times the path length. The path length was 4 decimeters. Sorry, 4. So if you multiply all, you are going to get a concentration of 0.05 grams per milliliters. A sample of 2-butanol has an optical rotation of plus 8.5 degrees. The specific rotation of pure plus 2-butanol is 13.52 degrees. I calculate the percentage purity of the sample, and I calculate the concentration of the solution that contains a 90% enantiomeric excess of 2-butanol. So let's start with the first part. For the plus 2-butanol, he says we should calculate the optical purity. So optical purity is equal to the observed angle of the observed rotation of the mixture divided by the observed rotation of the pure enantiomer and in this case it is the plus enantiomer, then times 100%. That is, so it is optical purity, which is measured in percentage. So this is the formula for calculating the optical purity of the sample in the first instance. and this is equal to, we were given the rotation of the mixture as 8.5 degrees. So this is plus 8.5 degrees. And then for the pure plus 2 butanol, it was given as 13.52 degrees. So divided by 13 point, it was also plus, so plus 13.52 degrees times 100%. And this is equal to 62.9%. So this 62.9% is the optical rotation of the plus 2 butanol. This means that in the first place, in the I part, the enantiomer in excess is the plus, and then the one that is in the racemic mixture is the minus enantiomer. But in the second part, it says that calculate the concentration of the solution that contains 90% enantiomeric excess of minus 2 butanol. So this, the second part and the first part, are two different questions. However, they have one thing in common. The thing they have in common is the path length. Both measurements were carried in the same tube, and therefore they have the same path length. So let's write the formula for calculating the specific rotation of a sample. Specific rotation is equal to the observed angle of rotation times divided by the concentration times the path length. Let's make the concentration and path length the subject. So concentration times the path length is equal to the angle of rotation divided by specific rotation. But the angle of rotation divided by the specific rotation is the same as what we found in the first instance, which is the same as the optical purity of the mixture. And this optical purity is also referred to as the enantiomeric excess. So in the second instance, the enantiomeric excess or the optical purity was 90%. And then in the first instance, it was 62.9%. But remember that in this part, we are calculating for the plus enantiomer. And in the second part, which is II, we are going to calculate for the minus enantiomer. So this implies that the concentration of the plus enantiomer times the path length is equal to, it was 90% enantiomeric excess, so it's equal to 90%. And in this instance, this is the minus. So this implies that the concentration of the minus enantiomer times the path length is equal to 90% enantiomeric excess. So here's 90%. Then in the first instance, we did for the plus enantiomer. So the concentration of the plus enantiomer times the path length is equal to 62.9%. But now, you see that the path length of both enantiomers are equal. So since they are equal, then we can divide. So let's assume this is equation 1 and then this is equation 2. So equation 1 divided by equation 2, which is going to give us C minus times the path length divided by C plus times the path length is equal to 90% divided by 62.9%. So the path length can cancel out. But in the second place, we are looking for the concentration of the minus enantiomer. So the concentration, this implies that the concentration of the minus enantiomer is equal to 90% divided by 62% is equal to 1.43 times the concentration of the plus enantiomer. However, in the question, we're not given the concentration of the plus enantiomer, and therefore this is the farthest we can go in this solution. The plus enantiomer of a compound A has an optical rotation of 125 degrees, if a pure sample of compound A has an optical rotation of 100 degrees, what is the composition of the sample? Alright, so the plus enantiomer has an optical rotation of 125 degrees, and then the pure sample has an optical rotation of 100 degrees. The question is saying we should find the composition of the sample. In other words, the percentage composition of the plus enantiomer and then the percentage composition of the minus enantiomer. But we can do this by first finding the enantiomeric excess. So the enantiomeric excess, percentage enantiomeric excess, is equal to the observed rotation of the sample divided by the observed rotation of the pure enantiomer times 100%. So this one times 100%. Let's go ahead and calculate. Enantiomeric excess is equal to the observed rotation of the sample is 100 degrees divided by the observed rotation of the pure enantiomer, in this case, which is the plus enantiomer, is 125 degrees times 100%. And if you compute this, you get 80%. So this implies that the plus enantiomer is in excess of 80%. What does this mean? Since the plus enantiomer is in excess of 80%, it means that the racemic mixture has a composition of 30%. But we know that the racemic mixture is made up of an equal moles of the plus and then minus enantiomer. In other words, we need, in order to be able to find the amount of the plus enantiomer and the plus and the minus enantiomer in the racemic mixture, we need to divide the 30 by 2. So 30% divided by 2, which is equal to 15%. So let's find, so it means that the minus enantiomer has a composition of 15%, and then the plus enantiomer has a composition of 80% plus 15%, and then 80% plus, sorry, I made a mistake. 80 minus 100 minus 80 is 20%. So here's 20. And therefore 20% divided by 2 is 10%. So the minus enantiomer has a composition of 10%. And then the plus enantiomer has a composition of 80% plus 10%, which is equal to 90%. A pure sample of the naturally occurring chiral compound A is 0.05 grams, is dissolved in water of 2.0 mils, and the solution is placed in a 0.5 decimeter cell. 3 polarimetric readings are recorded with the sample: 0.625 degrees, 0.706 degrees, 0.682 degrees. What is the specific rotation of the sample? So we need to first find the average degrees of the reading and the absolute. So we need to first find the average observed rotation. So average observed rotation is equal to, we need to just sum these rotations and divide by 3, which is equal to 0.625 degrees plus 0.706 degrees plus 0.682 degrees divided by 3. And this is equal to 0.671 degrees. But we know that in the question, the path length was given as zero point 0.5 decimeters. And also, we can calculate the concentration because we're given the mass, which is 0.05 grams, divided by the volume. And the volume is 2.0 mils. And that is equal to 0.025 grams per mils. So the specific rotation of a sample is given as the observed rotation divided by the concentration times the path length. And the observed rotation is what we calculated here, 0.671 degrees divided by the concentration, 0.025 times the path length. And the path length was given as 0.5 decimeters. And all of this is equal to 53.68 degrees. The student has prepared compound D in lab. She is sure that the compound contains no impurities. A number of physical analyses have confirmed the structure of purity of the compound. A sample of compound D, zero point 0.1 grams, is dissolved in methanol, 2.0 mils, and the concentration is placed in a 1.0 decimeter cell. Three polarimetric readings are recorded with the sample, which is 0.995 degrees, 0.904 degrees, 0.936 degrees. A. What is the specific rotation? B. What is the optical purity of the sample if the optical rotation of D is 25 degrees? C. What is the enantiomeric excess of the sample? D. What is the composition of this sample? E. Why did the previous analysis show that there was only one compound present? Alright, so from the question, the path length L is given as 1.0 decimeters. We can calculate the concentration because we are given a zero point 0.1 grams in 2.0 mils. So concentration, which is mass divided by volume, is 0.1 grams divided by 2.0 mils. And this is equal to 0.05 grams per milliliters. Sorry, so this is equal to 0.05 grams per milliliters. And we can also find the average observed rotation. And this is equal to, we just sum all of these values and divide by 3 because there are 3 values. 0.995 degrees plus 0.904 degrees plus 0.9363 degrees. So let me write that here. Plus 0.9363 degrees. All of this divided by 3. So this is equal to 0.945 degrees. We can then go ahead and calculate the specific rotation, which is the observed angle of rotation times the concentration divided by the concentration times path length. And this is equal to 0.945 degrees divided by 0.05, the concentration, times the path length. And then the path length was 1.0 decimeters, so 1.0. And this is equal to 18.9 degrees. Then the B part says that what is the optical purity of the sample if the optical rotation of D is 25 degrees. So optical purity is equal to the observed rotation of the mixture divided by the observed rotation of the pure enantiomer, so in this case D, times 100%. And this is equal to the observed rotation of the mixture was what we got earlier, 18.9 degrees divided by the observed rotation of D is given as 25 degrees times 100%. And this is equal to 75.6%. C. What is the enantiomeric excess of this sample? Enantiomeric excess is the same as the optical rotation, and this is equal to 75.6%. And then the D part is, what is the composition of this sample? Now, to find the composition of this sample, we have found the optical rotation as 75.6%. It means that the racemic mixture is 24.4%, and therefore we will have the major enantiomer. Let me represent it, which is the one in excess, as 75.6% plus 24.4% divided by 2. And this is equal to 87.8%. Then let me do the minor enantiomer somewhere here. It's going to be 100% minus the 24.4% divided by 2. Sorry, it's 100% minus the major enantiomer, which is 87.8%. And if you do that, you are going to get 12.2% for the minor enantiomer. And then the last part of the question says that E. Why did the previous analysis show that there was only one compound present? The reason is because enantiomer differ in how they interact with plane polarized light and not in any other physical analysis. Because the question says that she did a physical analysis. You don't use physical analysis to determine the enantiomers present in a compound except you do polarimetry, or you determine the optical rotation of the compound.